maybe this could work backwards to a function that generated both of these. I check the other derivative. If they agree, if the second mixed partial derivatives agree, that means they came from a generating function. And I don't know if the books uses the word generating function. That terminology is used in a lot of different places. I use it here because what generated this dE might be a function that I took a derivative, a total derivative of. So I call it the generating function. Okay. Is everybody semi with me? So the whole idea is, if the mixed partials agree, there is a function f that came from. So then I have a process I can go through to get that. So take a minute, check the mixed partial derivatives. Just to make sure we're all on the same page, which part of that is what we call the m function?
X cubed plus
Yeah,
y cubed.
so this is the m, and this is the n. We all understand it doesn't really matter, but the way that we set up the process, I want to call the dx piece m and the dy piece n. Yeah. Let me catch up to you. So here I'm going to check my. What's this guy's partial? 3y squared. And here I'm going to check nx. 3y squared. So when I do my, that means y is the only true variable. I'm treating x as a constant. When I do nx, same thing, just vice versa, right? So there's not a lot to... All right, there's a ton to partial moves. In terms of what we need for this course, that's about it. That's the level we go to. Is there a lot more you could do with partials? Anybody ever work with partials? Yeah. In fact, there's a whole other semester, at least class worth, of partial differential equations, right? So we're going to do a process today that if the simplifying assumptions aren't true, we cannot do it at this level. We would need a PDE class. But of course, it's going to be true for us in this class, right? This is kind of the way it works. I'll show you one where it's not true. I think I made one. So what does this mean? This fact that we just got this. What does that mean?
They came from a common function.
Good. So there, f exists. I don't have to. We haven't talked about this yet, but if that wasn't true, I could try to do an integrating factor that would make it true. You guys with me? There might be a function I can multiply by. I'm going to show you an example of why that might be true, right? I know when you're first seeing this stuff, it's got to be weird. Why is there necessarily a function I multiply to make things work? Why would that even be something I would think about? And I'm going to show you a concrete example of why. And doesn't that sound nice? Sounds great. It's like, Jeff, yes, concrete. Please, dear God. The higher you get in math, the more you find yourself going, give me an example. Give me all right. So f exists. How do I start to piece f together? Since f exists, this means the criterion is met. It is exact. And what that really means is there is a function f so that I can find the solution of this form. A solution of this form exists. Okay. So what's the first step? How do I start to try to work my way back to what this guy is? Yeah, what is this related to f? So you get started?
Partial of x.
Yeah, so if I say, so I know m is the partial of f with respect to x, right? So I'll need that, yeah? And m is x cubed plus y cubed. I can get an expression for f, obviously not fully determined, because of course the partial considers what to be in this case, the partial with respect to x considers y to be a constant, correct? So this is the part that's really tricky, but is a perfect analog to 180. In 180, the only constant that could be a constant was a freaking constant. That's a weird statement, but I don't care. That's why you put plus c, plus c, going crazy, all right? This is the first place we see where we have to put a function of, in this case, y, because according to that partial, that's a freaking constant. So let's see, what do we get? So when I integrate this with respect to x, what do I get?
1/4 x.
1/4 x to the fourth plus
Plus x times 1.
xy cubed plus
F of y?
g
Or g
of
of
y.
y.
Don't use f because I already use f, right? Okay. Convection. I know at least one of you has done homework from this section. I don't know if anybody else has tried this section yet. You're like, dude, slow down. All right. So that's great. I have the answer, except for part of the answer is still unknown. But I'm a lot closer to the freaking answer. I've got the format of it. What's the next step?
gy.
Yeah, I use the other piece of information I was given. Now, real quick, it does not matter worth anything which piece of this I integrate first. I just chose m just because it was the first damn thing, right, guys? It does not. I could have integrated this with respect to y. So what I do now is n is equal to what related to f? Partial of f with respect to y, correct? You guys with me? So if I just take the partial of this with respect to y, I can sort of compare it with what m is. That's the whole idea of an exact. Exact is definitely more complicated than the earlier ones. Linear was more complicated than separable. Separable is stupid easy. And so it kind of makes sense. We just keep growing. So today's lecture, you're ready. Okay. So what is the partial? What happens here with respect to y? This guy dies. This guy becomes 3xy squared. And of course, this guy is just g prime of y. Now comparing n, because that's what this is, and is this, what is g prime of y equal to?
2.
Everybody see that? That's too nice to believe. I'm sure somebody out there is like, none of this is too nice to believe, Jeff. So g prime of y is 2. All right, now extra paper. So what's g of y?
2y.
Bullshit. So then what's f?
1/4 times x to the 4th.
Yeah, so I've already got this piece. 1/4 x to the 4th plus xy cubed plus
2y.
2y. Now that's what f is. I really need to make a point out of this. Okay. All of that work, I need you to get to a point. I need somebody out there, at least one person, just do this, Jeff. There you go. I need at least one person to go, okay, that was relatively easy. Are there kind of a lot of parts? Yeah, but there are just a couple things you have to memorize, and then they kind of flow from each other. If you just memorize f is what both things came from, I'm just kind of undoing it one piece at a time, using all the information that was given. Let me stop for a minute. So if you look at an exact, if it is exact, the coefficient of dx is giving me information about f. Second coefficient of dy is giving me information about f, and I used both. That kind of makes sense. That is not the solution to the dE, though. I need you to understand that is not the solution to the DE. And you're like, what? We did a lot of work, Jeff. The idea, that can't be the solution to the DE. Does the DE have anything about freaking F in it? No. Does anyone know what the actual solution is?
C is equal to.
Yes, that equals C. So the whole idea from the beginning was, what would generate this equation if I had a function that was equal to a constant, because that would make that side 0. So I figured out what that function is, and now for the answer I just have to say it's equal to a constant. Okay, maybe.
What's the G, function?
I love it. Just like in, I really need you guys to get this. Just like in Math 180. Am I doing is everybody cool with where that F came from? This guy. This guy right here. Up to the GY, right? Absent the GY, is everybody cool with that F? Okay. So what the shit is that? Well, what did I do to get to F? What did I do? I took the integral. In Math 180, you were doing a total integral, meaning it was a hard dx, right? Not a partial. Therefore, the only things that are constants when I have a hard dx, right, would be an actual number. That would be the only thing that's a constant. So I would just add a plus c. So everybody sort of. So when I integrate some function, an indefinite integral, I put a plus c to cover my ass for the fact that a derivative happened, and I might have lost information about whatever constants were there. Agree with me? If I have a function, for example, that looks like this, x squared y plus y, and I take the partial with respect to x, what do I get?
2xy.
2xy. What happened to this guy?
Constant.
Constant according to this. So if I integrate this, I have to put x squared y plus a constant, but it's not really a number constant, it's a frickin' function constant. Because the partial looks at any collection of y stuff as constants. Does that make, it's exactly the same reason we put plus c. It's weird as shit when you first see it, but it's the exact same reasoning. We gotta cover our ass for any constants that might have been there. And what's considered a constant when I do partial with respect to x is any function of y. So I just collect it all right there. You guys okay out there? Semi-okay? So this step right there is actually, is basically very close to Math 180. I just did a direct integral of that, but I just considered y to be constant. So instead of plus c, I have to put plus gy. Do you have to use g? I don't care, right? But we just use g because we already have f. Okay. How's everybody with that? Are you guys okay? All right. Yes?
Do we have to do a partial because the x and the y are together in a term? Like, why are
So-
we doing a partial?
Okay, real quick. It's not that we have to do a partial. It's that a partial was done to get to that expression. If the criterion, if Clairaut's theorem works, if I get the mixed partials equal each other, that means there was an f that I took a total derivative of to end up there. And real quick, let's write this down. I'll do it up here. Do it live. Are you? Yes, you are. What is a total derivative? Okay, let's do this. So if I take a total derivative of this, it's going to be the partial of f with respect to x dx plus the partial of f with respect to y dy equals, in this case, 0. That is a total derivative. You have seen this before, you just didn't necessarily write the partial stuff down. Okay, maybe. This is not the exact. This would be exactly exact. What do we call this? We call it m. And what do we call this? Yes?
Are we gonna get to the point where we'll have like a dy dx and we'll have to end up rewriting the equation in order to make it into two partials?
Sure, yeah.
Okay.
Alright, so here's where we're getting to. So chapter 2 is piece by piece, here's a form, work with, here's a form, work with. You know, on this first test, I'll write this up in a minute, and on the next quiz, which is gonna be this Thursday. Alright. You're welcome. Let's see. You guys are high enough up in your college years. You guys all understand the more grades, the better by now? Some students don't understand that. I think I told you about the class where the only grade was the oral final exam, yes? You don't want that. You want a lot of grades. So you're welcome. The next quiz on Thursday. But I'm just gonna go 2-1 through 2-4. 2-5 is, 2-5 was. There it is. Let's see. What was 2-5? 2-5 was substitute. Sorry, that's what we're going to talk about today. 2-4 goes through exact, right? So what's going to be on this quiz? There could be direction fields, phase portraits, right? At this point, looking back at those, okay, give me those. Direction fields, I'm not going to make you draw them completely by hand. I gave you that. Pretty sure I put it up on Canvas, the website where you can. Did I? Was I nice?
Yeah.
Okay, I'm trying to remember to be nice. It's not automatic for me. And then 2-2 separable, 2-3 linear, 2-4 exact, right? So it's going to be on this. And I'm going to put a very basic exact, because today we're going to talk about what if it isn't already exact? Can we make it exact? That's where we're going to start today's new stuff. Okay. I was saying something else before that. That was a side note. What was I saying? Shoot. You're all like, oh great, this guy should retire.
What we're building up to?
Yeah, so all of chapter 2 is method, right? I'm going to give you a bunch of DEs, and I'm going to say solve. And you're going to have to determine which method would work in which time. And I might not have it in the exact form it's supposed to be in, correct? Sort of like I give you some equation and say, find the center and radius of the circle. And it's not in the right format, you just got to put it in the right format first, correct? Same idea. Are you guys with me at all? So yes, one level of knowledge in any math class is how does each process work? And the next level, which is often the hardest level, is when do I do which thing? Right? That is always the hard. I know how that works. When the shit do I do that, Jeff? Right? All right, that's part of what you got to figure out. Yeah, okay. Is that all right? I don't know if that helped at all. That probably made you feel worse, but oh well. Okay. Sorry. I'm not trying to make you feel better. I'm trying to get you ready for what's coming. Okay, so let's talk about what do we do if I have something that I can maybe make exact, but it isn't currently exact. So what would it mean for a differential equation in this form? Real quick, what would it take for this to not be exact?
The partials be different?
If the mixed partials are different, exactly. So let's do this. Let me see if I made one that would be so nice if I made one for myself. Yes, I did. Kick-ass. This is an interesting example. I think I have another one somewhere, but screw it. Here's an example of a DE that is not exact, but I could do it a different way. So I got another one somewhere, but just if I start with, was it just, where'd it go? Yeah, it's just that, okay. Let me do this, okay. All right, start with that. Can you take the total derivative? It's sitting right up on the monitor for you. Right, maybe I should probably be recording what I'm doing. Seems like a generally good idea. Do the total derivative of this. And I'll take a minute to show you you've done this before. All right, so what's how does that work? How do you do the total derivative? It's right there on the monitor. So here's my f of x, y, correct? Okay. So what do I do with it first? Partial with respect to x. Yeah, so what's that? And then I'll do the other side. Yeah. A couple things, real quick. Let me see. I'm just going to throw this little side note. Might not even want to necessarily write this down, but real quick. How do I do implicit differentiation here? It's so much better, Jeff. Thank you. Yes, it'll be 2xy plus x squared y prime equals 0, correct? And this is 2xy plus x squared dy dx equals 0. If I multiply by dx, I get there. You guys all with me? You have done partial derivatives. We just didn't tell you that's what you were doing. This first thing, this right here, didn't you treat y like a constant? Of course you did. Because it's a product rule. It's this piece of a product rule. But now you see how partials are actually in there. Maybe. Now the ultimate thing, the thing I would hope most of you guys would do, is just frickin' solve this shit for x, yes? And you can write it like this if you want to. And then what's the derivative? Yep. All right. Which looks different, but actually if you solve for dy dx, you'll eventually get there plugging the y back in. Are you guys semi with me? So this is a very simple equation, not a lot going on, so there's multiple ways I can kind of look at it simply, right? Coming back to this, at the moment, the mixed partials agree, correct? What's the derivative with respect to y partial? 2x, yeah. And what's the derivative with respect to x partial? 2x, okay. But looking at this, what could I do? How could I simplify this? What can I divide by? X. So then I would get 2y dx plus x dy equals 0. Is this exact? No. What's the partial with respect to y? 2. What's partial with respect to x? Oh, shit. Do you guys see what I'm saying? So real quick, the only reason I wanted to do this was to show you why might there be something that is exact, but not the way they gave it to me. It's missing some multiple, because I could have divided by something. So that's why it's missing something. Do you guys see what I'm saying? So somebody took a derivative, blah, 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 divided by something, and it lost it. And I'm like, oh shit, I got to figure out what to give it to make it exact again. Okay, that's basically what all integrating factors are, is what does this need to become the right form, right? Okay, stop. One thing that does suck a little bit, what letter do we use for integrating factor?
Mu?
Mu, right? Mu of x. Today we're going to get into solving differential equations with substitutions. And of course the substitution we use is u equals something. And they look very similar, don't they? Oh, shit. All right, well these things happen. Okay. So that's just, now real quick. That's an example. It's a very pathetic example, but it's a nice, quick, easy example. Why would I not even freaking try to make this exact? I wouldn't even do it, especially once I show it to you. It is not what most people call pretty. But why would I not even try to make this exact? What is it at the moment? It's a much better thing. This, if I try to solve this, like I didn't know this shit, and I want to solve this. What is this? Separable, yeah. Solve it real quick. Do it. just slide everything over there. Shit. You guys cool with that first step? That's the whole idea of separable. I can get all my y stuff together, all my x stuff together. What's the integral of both sides? Ln y. Cool. What can I do with this? Pull it up here. And then I can raise both sides, e to both sides, right? So then I get y equals e to the ln x to negative 2 plus c. Let's call this c1. Let me stop for a minute. There. Of course, here these kill each other, right? So you got y equals x to the negative 2, and then I have, are you guys all comfortable with that becoming this? Because this will be e to the this times e to the c1, which itself is a constant. And if I just multiply both sides by x squared, I'll get back to, of course, where we started. Are you with me? Not quite where we started, because they didn't give us enough information. I'd have to say, for example, I could say y of 1, oh, who knows? Y of 1 equals 7. Yeah. Yay. And then I could figure out what c was. Okay, so everybody that was just a nice little review of separable. So dear God, if I don't say to use a specific method, you rule out separable, right? Just like in Calc 2, you rule out u sub before you try and start doing some weird ass thing. Okay, maybe. Okay. Now, I made a very nice generating function that gave us the DE that I could do using separable. Will that generally happen? No. No. The function could be gross, and it could still lose some parts. I think somewhere I've got an example, but we don't have time. It would just be an example where it wouldn't be separable. I could divide by x and y or something, and it wouldn't be separable. So I need to figure out how to make it exact. Okay. So if I have a DE in this form, and it's not currently exact, I kind of assume there's a mu that I could multiply by that would make this become exact. Yeah, this gets kind of funky. Blah, 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 blah. Okay, yeah. So let's see, if I have so mu is going to be a function of xy, m is a function of xy, n is a function of xy. I'm not going to write the of xy anymore. Is that cool? Okay, just want that understood. So if I multiply everything by mu, so this is really interesting, at least to me. I could be the only one, which I'm used to. I need you, so do I know what mu is yet? No. I'm making a lot of assumptions. I'm assuming there is some function that I can multiply by that will make it become exact. And you should all be comfortable with what we're about to do. Here's the DE. Let's apply the criterion. What would it take for this to meet the criterion? What do I need to do? What do I check to see if this is exact?
Partial derivatives.
Yeah, good. So the partial of what?
Of n.
Now what's funny is if you said I could say you were. So the partial of with respect to y. And I check to see if that's equal to the partial of the partial of the un with respect to x. Sorry, that is the criterion for exactness, correct? This is sort of what we did, not quite. So we're assuming mu exists. and then we're going to follow the path down and see if what it would take for this criterion to be met. And we're hoping it gives me a way to figure out what mu is, right? Can somebody, all right. Shit. All right, okay. What would it take to take this derivative? What would it require? What rule?
Product.
Because these are both functions of x, y. I just got tired of writing that shit, yes? All right, so let's do this. What's the partial of mu with respect to y? How can I write that? Nice. I could write d, or I could write mu y. Is that cool? Leave the other dude alone, correct? It's just product rule, right? Thank God the rules are the same for the most part with partials. All right. Plus, now I leave mu alone. My, okay? Same thing over here, correct? Are you guys all okay? So again, part of your brain could be like, why can we do this? Because why the shit not? Of course I could do this shit. How do I know that it exists? I don't know yet. Assuming it does, this is what would happen. So then let's just follow it. Let's just see where we get to. Okay, which again, you don't get to do very much, but you guys, some of you guys took like Cut 3, you get to do it a little bit more, but you don't get to play with the shit too much. Equals, what am I up to? Oh, this is this, okay. Equals, and then on this side I get mu xm plus mu mx. N. I had the in my head. Yes.
Are those x's and y's subscripts or
Yeah, okay. So just to remind you guys, so if I do the partial of f with respect to x, that is f sub x. Yeah. And if I do the partial of that with respect to y, yeah. The subscripts just make it easier, so I don't have to, no, if you like to make this symbol, you can, it's fine. All right, so what can I do with that? What is it that I'm trying to solve for? What is it? Yeah, I'm sorry.
This might be a stupid question, but shouldn't one side be negative if you move to the other side of the equation or not?
Oh, I didn't take, okay, sorry. So let me make sure that I did. So here's the DE. I'm applying the criterion, the mixed partials have to equal each other, right?
Oh, okay, sorry.
That's all, yeah, that's my fault. This is the given DE, I'm applying the test. I didn't do anything to this equation, I'm just applying the test to it. Okay. Good question though. Of course, what am I trying to solve for? What is the thing that I assumed existed? Mu. All right, so how can I solve this for mu?
Good question.
Say again? Factor it and crying? Okay. Crying could be a part of the process. This is true. Failure is always an option because that just means you know which path doesn't work.
Get all the mu's on
Get all of these shit together. Okay, that's a good first step. So let's see. Mu my minus mu x. It's a little cold medicine commercial up here. Equals mu x nuxin minus mu. Okay. Now, real quick, here is what I talked about earlier. This is horrendous. Correct? And I could factor mu out and divide, but before I do that, I'm going to make a simplifying assumption. This is what I was saying earlier. There are some things that could become exact that are going to be out of our reach. And as a math student, I remember this being very frustrating for me. As I went up, I was like, okay, now I understand that, but now I know there's this whole set of other things I can't do yet. Get to the next level. Okay, now I understand, but there's this whole set of other things I don't know yet. So I don't know if anyone's felt that way yet. So yes, once you're done with this class, there's going to be a whole set of other shit you don't know yet. But we got a whole lot of shit that we do know. I don't know if you guys would. So here is where I make some simplifying assumptions. What that means really is, like I said, there will be some times when the assumptions are not met, I can't do shit. Can't. I need to know more about partial derivatives in order to do something. So here's the assumptions I can make. Let's make them one at a time. Assumption 1. I can make the assumption that mu is only a function of, let me not use f, let me just use the word, function of x. So I can, sort of like the example I gave us, remember, do you remember the one I gave us, x squared y equals 7? What was that I divided by? I divided by x. That would be the missing function. That would have been mu. I should have made a bigger deal out of that. The earlier problem we did, x squared y equals 7, blah, 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 blah. And then did we divide by x? So that would have been the mu function. If I would have done the process we're about to create, it would have told me mu is x. That's what you're missing. Multiply by x, it becomes exact. Beautiful. So this assumption works a lot. But it also doesn't work a lot. Okay. So I could assume mu is a function of x. So what does that mean mu y equals? 0.
0.
Kick ass. So then what happens? Oh, you're going to love this. All right, let's see. There's just not enough room for this. Let me see. All right, let me turn off this guy. And yeah, I'm going to go over here. By the way, I remember I was in a classroom. There were chalkboards all the way around the campus. Our teacher would start over that end, and we'd all turn around our chairs. Right, we follow him, and we follow him. And then we go, what happened over there? And he'd run across the room and say, Anyway, sorry. So I'm not quite to that point yet, but getting close. Looking at assumption 1. Let's see what that leads us to. What is our little, where we are now, what's it become? UMY minus UMNX, Jeff, equals, mu x is mu x, so mu x n. But let's replace this with something better. Can somebody tell me what would mu x be? Is it really a partial if it's just a function of x? It would just be a d mu dx. Right? It's not a function of two variables anymore. I don't need partials. Are you guys kind of with me? Okay. So equals d mu dx n, and of course the other piece becomes
0.
0. Okay. Now, real quick, I just want to remind you guys, this is going to happen a lot. We are in the middle of a derivation. We're going to get to a point at the end, which is where we're going to kind of like jump to every time we do a problem like this. Are you with me? We're deriving the process. You're not going to have to do this every time. Every class I teach, I have to say that, right? But I understand it. From your perspective, you have no idea. What the hell am I going to do with this shit? Okay. Well, all right. So let's do this. Mu my minus nx equals d mu dx times n. Does anyone know what form that's in? What form of dE that is? It's not quite separable. Linear? Yeah, linear. All right, let's do this. So let me put d mu dx. Let me divide by n. Let me do this plus. Let me see if you guys are cool with this. I'm doing too much at once, but let's see if you guys are cool. Okay. So I subtracted that over. So I just turn those around. Is that cool? And then divided by n. Okay. You guys see how that's linear? Do you guys see how it's not separable? Hell no. Real quick, what is that a function of? Oh, this is such a weird question, I know. What is that a function of? X and y. I know I'm taking a partial back to x, but it's got x's and y's in it. It could, right? So what I have to assume it's going to be a function of x and y. That's a function of x and y. There's no way in hell this is separable, right? Maybe. If this is separable, though, there was probably an easier way to do it from the beginning, to be honest. We're still not to the point that we're gonna just shortcut to. We're still deriving shit. Are you with me? So none of this is anything you're gonna have to do ever again. Okay. How do I solve, this is a beautiful review. How do I solve linear stuff, linear equations?
Integrating factor.
Yeah, oh my God, right? Oh, you're gonna love this shit. Okay. Yeah, okay. I'm gonna erase all of this, yeah. Good. Because assumption 2, what do you think assumption 2 is gonna be? Assume that mu is a function of y, it's gonna be very similar shit, so I'm just gonna jump to the chase at that point. Are you with me? Okay. I'm gonna erase all of this. So let me write down just a general linear function, linear differential equation. And you guys remind me. What was the process to figure out the integrating function? Yeah, e to the integral dx. That's the integrating function, right? And that makes this become, you guys remember? Which this is, of course, separable. Okay. Now, again, just reminding us, you're not going to have to do this multiple steps. There's multiple forms, but we're getting to the point where we have a shortcut. Okay. I know I've said that many times. So I've got this business. What is p of x here? Yeah, nx minus my over n. Now, there's an assumption happening in here, correct? Oh. So then what would the integrating factor be? D. So what's it going to be? What was it up here? Yeah, why was it dy, Jeff? Come on, Jeff. Be better. Okay, my fault. So this will be dx, right? Now, real quick. If I use this integrating factor, I make it become, well, let's try an example. Let's get a concrete example. The other way I could go, if I make assumption 2, if I assume that u, and of course, let's see if I can do something better than this. What did I use different symbols in my, give me a second, guys. This is where things get really weird. Oh, yeah, okay. I think somewhere that I turned something around. Give me a second. Which one am I doing right now? That one, okay. I assumed that was a function of x. Okay. Got to here. Sorry guys, give me a second. Something got turned around, let me think. Of course I erased a lot of stuff, let me see. That was fine. That was fine. Yeah, where, I think that might be where it is. Let's see. Yeah, okay, so there, yeah, okay, that's true, okay. Okay. Thank you for being patient, everybody. This gets a little trippy, as you can tell. sure I've got this right in the first place. Here we go. Oh my god, okay. I need glasses, let's see. Oh, there's no way in hell. Here, let me put this up here. Bum, bum. Don't get old, please. Alright. Oh, there, I can see it. Alright. Let's see. Alright, let me make sure I ended up where I wanted to be. So here's where the simplifying assumptions go. Let's see how they do this. Where did they do their assumption? Oh, here it is, okay. U is dependent on X, I like it. They get to here, which is, okay, sorry guys. So right here, does that match up with, it basically does, I just had everything on one side, right? Yeah. Okay. Okay. And then the other thing that can happen is, all right, let me turn this off. I think I see where something went freaky. The other thing I was kind of implying is we're assuming also that these are functions of x alone also, right? In order to be able to do that last step. I think somewhere, where would I have done this?
Or maybe like divided by n, and then the subtraction has to be.
I don't see up here where I went wrong, because that's what I need it to be. Sorry, guys. I think when I try to do it myself, I lost a negative or something.
Yeah. Oh. It has to be equal, not plus. Well, dy dx times n is on the opposite side of the equation. So shouldn't that be negative when it goes over?
No, I distributed the negative. All right, here, let me see real quick, I'm sorry. Yeah, so divided by n. Wait, okay, good. What do I have? N, oh my god, I gotta zoom in. I'm really sorry, guys. I always hate when this happens. It's always exciting to be a teacher and get lost in your own work. Nx, okay, good. Okay, good. Oh, but that's if it's, yeah, so somewhere All right. I'm sorry. I've already taken enough time. Somewhere I did not use my assumption correctly. So let me we're to the point where you can see at least the form it's going to take. Let me just give you the correct forms and point out the stuff that we're just to remind you guys, the stuff we already know. So I'm given this D. Right? So either I could use the integrating factor e to the integral, I've got a way to remember this, I gotta remember. What was the way I was gonna remember this? So when I was a student, because there's two of these suckers you gotta remember. So I'm gonna try to give you the way I remember it from when I was a student. So mu of x, if mu is a function of x alone, this would be, what way did I remember this? Yeah, okay. All right, this is exactly what I did. Oops. Is it Jeff? Is it really? I think that was right.
I think it's n.
Oh, it's N. That's right. Okay. And if mu is a function of y alone, it's going to be the reverse. And again, because, it's gone. When we did these these should be little subscripts down there. There we go. When we did the derivative and we assumed mu as a function of x alone, there was a minus mu y that was 0 if mu is a function of x alone. So if it's reversed, there will be a negative sign that's still there, which is why these are sort of the reverse of each other. Now, very quickly, or not quickly, let's not do anything quickly. So the way I remember this is when it's x versus y, m and n are in alphabetical order. And when it's y, they're reversed, right? Now the other part of this is remembering what goes on the bottom. I will do this. I will do this for you. I never make you memorize anything I don't have memorized. And obviously I don't have this memorized anymore because it's been a while. So I'm just going to give you these. It's enough work to do. So what are you given? You're given this. When do you have to do one of these two things? When the partials don't match up. Because then you might need, is maybe somebody divided by something that used to be there. I'm just trying to figure out what was it, right? So first check that. If it isn't exact, maybe you can make it exact. And then how do you tell which one of these you're going to use? I'll show you. Let's do a concrete example. All right. It kind of depends on, I want you to notice. See how this is supposed to be a function of x only? Which means this better end up being a function of x only, correct? This is supposed to be a function of y only, which means this better end up being a function of y only, correct? So what you end up doing, is everybody with me that I'm going to give you n in the problem, right? You're going to know what n is. Given this problem, can you figure out my and nx? In fact, you will already have to check to see if it was exact in the first place, right? That's kind of beautiful. The work you already did is going to be used, correct? So all this shit in here, you know, or you can get very easily, right? Yes?
So this is basically just like solving a linear problem.
Yes. By making an assumption, we can force, and by multiplying by a certain, that function, we can force it to become linear, and then this is how you solve a linear, yes. But then the shortcut we create is just to go straight to this, and then we can go from there. So let's do an example. Let's see, blah, 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 blah. Oh. Let's see, do I want to do that one? No, I don't want to do that one. No. Yeah, let's do this one. Okay, good. Alright, so here comes the concrete idea. The stuff you're actually going to do, which is always good to eventually get to. So let's say I've got, oh, this one looks nice and gross. Okay. Blah, 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 blah. Yeah, okay. Let's see if you guys, how you guys feel about this. All right. Is this, you already know the answer to this, but we have to do this anyway. Is this exact? Is this separable, by the way? Why, it's not? Isn't everything involving x and y, aren't they factors? Right? Is this whole piece dependent on y? Yes, is this whole piece dependent on x? Yeah. So do you see how I can just divide and multiply and get all my, so it's separable. Let's just pretend like we didn't know this. In fact, some of us didn't, so let's just keep going. Or let's say the instructions say, because Jeff's evil, solve this as an exact DE. Okay. Is it currently exact? How do you check? Here's my M, right? Here's my N. Make sure, be careful, they'll switch these sometimes, and in general it doesn't matter, but our processes are hardwired in M being dx and N being dy, so be really careful. So what do I check? What's the criteria? Sorry, go ahead.
Is sin x included in n?
Is sin x included in?
N.
Oh yeah, I'm sorry. Yeah. Did you move? Thank you. So what do I check? What's M? What do I check? M. Y. What's my?
Zero.
0. And what is nx?
Cosine.
Yeah, 1 plus 2y. That's a constant coefficient, correct? Times cosine x. So it's really easy to see those are not the same. Correct? So if I need to treat this as an exact, I need to figure out what piece was divided, right? That if I multiply by it, it makes it exact again. So what are 2 things I need to check? I need to check out this, and I need to check out this. Let's just do that. Let's just do that. Just do that by itself. What do I get for this guy? Is it pretty cool? Because these are my coefficients. I mean, my exponents in my integral. This piece would have to be a function of x. This piece would have to be a function of y. I can check both and use the one that that's true for. Do you see that? Okay, so my minus nix, what is that? Negative 1 plus 2 over y cosine x over, what's n? 1 plus 2 over y, become a thing, there we go. Sine x, that's nice, that just becomes negative cotangent x, okay. That's got, is that a function of x? Yes! Now just for shits and giggles, let's see, what do I get here? I'll get 1 plus 2 over y cosine x minus 0 all over m. That is a function of y. You could do it either way then. Sometimes only one of these will work. Sometimes both will work. Sometimes neither one. If neither one works, that differential equation is out of the realm of our class. Because it doesn't match the assumption we had to make for us to be able to handle it. Does that make sense? So it's always interesting when you have these situations where I need you to understand what's possible. Both of them could work. This is a situation where both work. Does everybody see why both work? I could do either one. Does everybody see why? Because this one needs a function of x, check. This one needs a function of y, check. I could do either one. Which one do you guys want to use? The y? Okay. I thought maybe that's where we go. I like that one person's thing cotangent, but that would have been that horrible, but you know, we could use the y dude. So then, therefore, this whole piece, I just throw in to this interval, right? Okay. Did I point at the right interval? Maybe. No, I did. This one. So mu, I now know that that will be just a function of y alone. E to the integral 1 plus 2 over y, dy. Gosh. Alright, I'm just not going to let it go. What the hell? I've got to look over and like whatever I made a mistake about. And of course, what does this become? Two, sorry, yeah, 2 ln y? Yeah. Okay. I like this. So that's mu. So therefore, here's what I do. All right, where'd it go? Jeff, you're so mean to yourself. Okay. Let me see. So already got this business here. I'm not going to erase the equation. now if I take the original equation and I multiply by this business, now I can simplify this a bit. How do I simplify this? Which way did I do it? Oh, I did
Square
that.
root of the y.
Or did I do it? Oh, I did it the other way. All right, let's see how this. I did it with the cotangent. Let's see what we get here. How do I simplify this? It'll be e to the y times e to this. If I pull the 2 up, the e and ln cancel, and I get y squared. So it'll be e to the y times e to the business. Pull the 2 up. The absolute value doesn't need to be in there. The natural log and the e cancel, and get y squared e to the y. Okay. So if I take this and then multiply by y squared e to the y. Thankfully that side's 0. Now that is exact. Yeah, good. Let's check if it's exact.
Is that the exact same answer we would have gotten if we had used cotangent?
What did I get? Let's see, sorry. We'll get the same answer, we just, it's definitely a lot, it's definitely a lot better if we would have used the cotangent. Too bad for us. Too bad for us. Yeah, we'll go. Did I? I did, thank you. I heard that. Let's see. Which one do we have? Yeah, it was just y squared. Yeah, okay. I thought to myself, how can I make this worse? Yeah, okay. Yeah, me too. Oh, thank you. All right, Jeff, let's try this again, buddy. All right. Y squared e to the y, 1 plus 2 over y sine x plus. All right. Let's check real quick if this is exact. The derivative with respect to y would be what?
E to the y times y
Well, it'd be,
plus 2y e to the y.
yeah, so it'll be 2y e to the y cosine x plus y squared e to the y cosine x. Because you have the product rule there, right? So that is my. What would nx be? Kind of nice, right? What's nx?
Y squared e to the y times 1 plus 2 over y cosine
Cosine x, right? Now if you distribute, there's your y squared e to the y cosine. And there is your 2y e to the y cosine, right? Same. Okay, okay. All right. God, rough day, sorry. I said, let me just do as many mistakes as I can. So now we can do this the exact way, right? Ooh, these are so good. How much work have we done already? And all the work we've done was just to get to a point where we could actually start doing the work, right?
Yay!
All right, so now I know that an f exists. So the partial of f with respect to x, I know that's equal to this business. No, not that business, Jeff. Let's try this again. This business, that's much better. So then I can integrate it. I'm going to have my plus g of y. And again, it doesn't matter which piece you start with. They both come from the same f, right? So what do you get when you integrate this?
Sin x.
Yeah, y squared e to the y sine x, right? Plus g of y. So the derivative with respect to y would be 2y e to the y sine x plus y squared e to the y sine x plus g prime of y. Just doing this a little quickly. And then I just compare that 2y e to the y oh, why did I do sine? Oh, today's just such a great day, Jeff. Oh yeah, because they integrate with respect to x. That's right. Oh, I'm comparing it to this stupid thing again. All right, Jeff, I love it. So I'll tell you something right now. It's a beautiful example of being nice to yourself. Identify what m is, and identify what n is. There we go, buddy. These guys I don't need anymore. Go away. Okay, comparing this to this, I get this piece is here, this piece is here. So what does this equal? 0. I love it. So which means g of y is actually just
C.
c. Yeah. A true constant. I love it. And we finally get f is just going to equal this business. So I get y squared e to the y sine x equals c. We can make it c1 just to be careful. Okay. Your form for any exact solution is going to be an f of xy equals c. So you're determining what f of xy is, and then you're setting it equal to a constant. Okay. Yeah, that was gross. If you do the cotangent, remember there was a choice we could have made. Believe it or not, if you do the cotangent, it is so clean. So, just like in Calc 2, you could kind of pick a route to go, and then you go, okay, that's looking gross. Let me try the other route, just in case it looks cleaner. And it's a ton cleaner if we would have chose the other way. But I was just curious what this would look like, and now my curiosity is sated completely. Yeah. Okay. One last thing in my waning minutes here. By the way, notice when you have an option, like what happened here. You won't always. So what is it that determines the two options? It was whatever these parts turned out to be, right? The nx minus my over n and the my minus nx over m, that one. They need to match up with the assumption made in each case. So the one that starts with m has to be a function of x, and the one that starts with n has to be a function of y. If they both are true, you can pick either one. Or sometimes only one is true, which means, okay, no choice, you just got to do it that way. Okay, I like it. I don't think there's any homework where neither one is true. That would be a little evil. Okay. So last thing. 2.6, I believe, is it? Or is it 2.5? Oh, 2.5, yeah. I just want to talk a little bit about the first idea in section 2.5.
So this was all 2.4?
Yeah, dude.
Okay, cool.
This is the last bit of 2.4, yeah. I don't think I gave you too many of these, because as you can tell, they are a little bit of a beast. Yeah. Keep that up there in case anybody's still copying. So here's let me start with a definition. Yeah, I don't know if I want to write all that down, it's just crap. Homogeneous, or homogeneous, heard it both ways. Which I was thinking about homogenized milk or something. Homogeneous, homogeneous, whatever way you like better. Function, what the hell is that? here's the technical definition of a homogeneous function. So if I have a function, let me use the same, yeah, okay. If I have a function of x and y just sitting there, and I replace x with tx and y with ty, in what I'm able to do, so this is the technical definition. What I'm able to do is take a t to a power out. Like this. So let me give you a very basic example. Yeah, let's use, here, let me just do, yeah, here we go. You'll start to see let me do a little bit different, yeah, we do this. Okay. You'll start to see an easier definition of homogeneous come out of our work. What happens when we replace the x with tx and the y with ty? What happens? So we replace every x with tx and every y with ty. What do I get? I get t, all right, let's just do this. Tx cubed plus tx times ty squared. So what do I get? T cubed x cubed plus tx times t squared y squared. So I can take a t cubed out, correct? And I end up with x cubed plus xy squared. And isn't that just the original function, right? You guys with me? Do you all see an easier definition for this? What kind of function would I call homogeneous or homogeneous? You can do it, you can do it. What's the degree of this term? What's the degree of this term? Third, good, right? Because the definition of degree is the number of variables I see total in a term. So I see 1x, 2y's, I see 3 variables. So as long as the parts are all the same degree, it will be trivially homogeneous. Are you guys with me? There's other things that are homogeneous, though. We got to be careful, because the idea of degree only really applies to polynomial terms, correct? Here's one more kind of thing that's homogeneous. Let me see if I can make it up. This will be exciting with your track record today, Jeff. Let's see what happens. There is one I'm going to do as an example. Let me see if I remember what it looks like. Shit. So it deals with this. Yeah, it doesn't matter, Jeff. Let's just do xy plus y squared. Do you guys all see, talking about degree of these doesn't make a damn bit of sense, correct? But what happens when I put a ty in for y and a tx in for x? The t's cancels. This piece doesn't do shit to me. It doesn't mess me up. And of course, these pieces are polynomial in nature, and they both have the same degree. So that will be homogeneous. I don't have to put all the shit in there. So we will see functions that are not polynomial. What you'll notice, another way to define this type of equation, and by the way, this is homogeneous equation. We'll do Bernoulli's in a minute. And also, very quick aside, there are two Bernoullis. So there's Jacob Bernoulli and there's the other Bernoulli. I forget his first name. David? No, it can't be David. It's probably right. There's two Bernoullis out there. They're not alive anymore. Sorry, they're somewhere. Is that okay? So you will see functions that are homogeneous, but they're not the same degree. It's not that idea, but that's a nice way to kind of like capture the idea for most functions. Okay. So don't forget quiz Thursday. I'm not going to put the stuff that we just went over today. I'm not going to give you an integrating factor exact. I'm going to give you a basic exact. You guys all. So I'm probably going to give you about 5 problems. And they're going to be identify what form it's in and then solve it. Okay. All right, guys. Let me know if you have any questions. Otherwise, I'll see you Thursday.
I have a quick question on the